In one of the first deep fields returned by the James Webb Space Telescope, an astronomer drew a thin cream ring around an unremarkable red smudge. The object looked like a smeared fingerprint. Nothing you would notice among the thousands of other faint galaxies scattered across the frame, the disordered blobs and half-formed spirals, the deep black pricked all over with light. The room was dark. The monitor was the only glow. She had been sent to find the first small galaxies, the ragged protogalaxies that theory said should populate the young universe, the modest little things that everyone agreed were waiting out there at the edge of observable time. What she circled was not small. When the numbers came back, they said this single red dot held more than 100 billion suns worth of stars, roughly what our own galaxy holds today, after 13 billion years of patient assembly, and this one had built them in less time than it took the Earth to evolve grass. Tonight we're going to spend some time with the galaxies that should not exist, the objects the Webb telescope found at the edge of observable time that are too massive, too bright, and too finished for the universe they are sitting in. We will look at what was actually seen, why it broke the models we had, and where the argument stands now, which is not where it stood 2 years ago. If you find this kind of slow exploration useful for sleep or winding down, a like or a subscribe genuinely helps, and I am always curious where people are listening from. Drop your location and your local time in the comments. One question is going to sit underneath everything else tonight, and I want to name it before we begin, because we will not get to it directly for a while. It is this: how does a telescope become a time machine? Not as a metaphor, as an engineering fact, because once you understand that, the red smudge stops being a photograph and becomes something stranger. Now, let us begin. The image that held that smudge came from a survey with a long name and a short nickname, the Cosmic Evolution Early Release Science Survey. It was one of the first large programs to use the Webb telescope's near-infrared camera after science operations formally began in the summer of 2022, and it was led by Stephen Finkelstein at the University of Texas at Austin. Early release science meant exactly what it sounds like. These were programs designed to be executed immediately, in the first weeks, partly to do science and partly to show the community what the instrument could actually do. The survey stared at a strip of northern sky near the handle of the Big Dipper, a region catalogued decades earlier as the Extended Growth Strip. It was not a random choice. That strip had already been studied by the Hubble Space Telescope for hundreds of hours across multiple campaigns. It had been mapped in ultraviolet, in visible light, in the near-infrared, by ground-based spectrographs, by X-ray observatories. If you wanted to know whether a new telescope was showing you something genuinely new, you pointed it somewhere that had already been exhausted by the old one. Hubble's view of that patch was deep, genuinely deep, the product of enormous effort, but placed next to what the Webb telescope returned, it was like looking through a rain-streaked window. In the new images, the faint became sharp, the invisible became merely faint. Thousands of galaxies appeared that no human being had ever seen, and most of them looked more or less as expected: small, blue, irregular. The kind of thing you would sketch if someone asked you to draw a galaxy that had not yet decided what shape it wanted to be. Then there were 6 objects that did not look right at all. They were not blue, they were red, deeply, stubbornly red, in a way that had nothing to do with the colour of the light when it left. The redness was a symptom of distance. Light travelling across an expanding universe gets stretched on the way, and stretching light means shifting it toward longer wavelengths, toward the red end, and then out of the visible range entirely. The bluest, hottest ultraviolet light from a young galaxy, if it travels long enough, arrives here as infrared. That is the whole reason the Webb telescope was built to see in the infrared rather than in visible light. It is not looking for warm objects. It is looking for objects so distant that their blue light has been dragged into the infrared by the expansion of space itself. So the redness told the astronomers that these 6 galaxies were far away. And in cosmology, distance is not a spatial statement. It is a temporal one. The light from these particular smudges had been travelling for so long that it left its source when the universe was only a few 100 million years old, less than 5% of its present age. Try to hold that proportion. If you compress the entire 13.8 billion year history of the cosmos into the span of a single human life, someone who lives to 70, then these galaxies appear when that person is a few months old, still in the cot, still being carried from room to room. They are infants, or they should be. The problem was never that they were there. Something had to be there. The problem was what they contained. The team that first measured them was led by Ivo Labbé, an astronomer at Swinburne University of Technology in Melbourne, working with collaborators across the United States and Europe. To estimate how many stars a galaxy holds when all you have is a smear of light a few pixels wide, you use a technique called spectral energy distribution fitting. The principle is not complicated, even if the execution is. You measure how bright the object is through each of the camera's filters, which sample different bands of wavelength. That gives you a coarse outline of the galaxy's spectrum. Then you compare that outline against libraries of models built from what we know about stars. How much light a star of a given mass produces. How that light changes color as the star ages. How dust dims and reddens the whole package. You find the combination of stellar population, age, and dust that best reproduces the colors you actually measured, and the mass falls out of the fit. It is an inference, not a measurement. That distinction is going to matter enormously later, but it is a well-tested inference. It had been used on Hubble data for 2 decades, and it worked. The results were not subtle. The 6 galaxies were not the dwarf-sized, 100 million sun objects that every simulation had predicted for that epoch. They were giants. The estimated stellar masses ran from around 10 billion times the mass of the Sun at the low end to roughly 100 billion at the high end. Our own galaxy, the Milky Way, contains something in the region of 60 billion solar masses in stars, and it has had 13 billion years and countless mergers to get there. Some of these objects, sitting in a universe that was barely 5% of its present age, appeared to be its equal. Labbé did what any careful person does when a result is too good. He tried to destroy it. He and his colleagues spent weeks pushing the analysis in every direction they could think of, changing the assumptions one at a time to see which ones made the galaxies go away. Make them closer and dustier. Make them older. Let a black hole contribute some of the light. Change the dust law. Change the star formation history. In each case, the data pulled back toward the same answer. The galaxies stayed distant, and they stayed heavy. How short a time are we actually talking about? At the redshifts these objects appeared to sit at, the universe was somewhere between 500 and 700 million years old. Call it 600 million. 600 million years is not a short time by any standard a human being can apply. It is longer than the entire history of animal life on land. It is more than twice as long as the age of the oldest dinosaur fossils. But it is a blink in the life of a galaxy. Here is the comparison that has stayed with me. The Earth formed about 4.5 billion years ago. Grass, the ordinary green stuff that covers lawns and verges and the hills around every observatory in the world, does not appear in the fossil record until around 66 million years ago, right around the time the dinosaurs ended. Which means the Earth spent roughly 4.5 billion years without a single blade of grass on it. 4.5 billion years of oceans and volcanoes and bacteria and ferns and reptiles and no grass. These galaxies assembled 100 billion stars in 600 million years, 7 times faster than the Earth took to produce a lawn. That is not a poetic comparison. It is an arithmetic one, and the arithmetic is the problem. To see why it is a problem rather than simply a surprise, you need the shape of the standard picture. Under the model that has organized cosmology for the past 3 decades, the lambda cold dark matter model, galaxies do not simply condense out of nowhere. They grow inside scaffolding made of dark matter, slight overdensities in the early universe, laid down in the first fraction of a second and imprinted on the cosmic microwave background, where we can still measure them, pull material toward themselves under gravity. They become knots. The knots are called halos. Ordinary matter, hydrogen and helium gas, falls into these halos, cools, sinks toward the center, and eventually becomes dense enough to ignite into stars. The growth is hierarchical. Small halos collapse first, because a small region of space has less distance to fall, and can overcome the general expansion of the universe sooner. Those small halos then merge into bigger ones, and the bigger ones merge again, and so on upward. Big things are made from small things, in sequence, and sequence takes time. That sequence has a hard ceiling built into it, and the ceiling is not a matter of opinion. Only about 16% of the matter in the universe is ordinary matter, the kind that can form stars. The rest is dark matter, which does not form stars, does not clump on small scales, and does not radiate. So when a dark matter halo of a given mass assembles, the absolute maximum amount of star-forming material it can possibly contain is 16% of its total mass. That is not a modelling assumption. It is a budget, measured independently from the cosmic microwave background and from the abundances of light elements produced in the first few minutes after the Big Bang. In practice, galaxies never come close to spending that budget. Some of the gas never cools, some of it is heated by the ultraviolet light of the first massive stars. A great deal of it is physically blown back out of the galaxy by supernova explosions and by the winds of massive stars. In the nearby universe, the fraction of available gas that actually ends up locked into stars is typically a few percent. Not 16. A few. So run the sum for one of these objects. A galaxy with 100 billion solar masses in stars at 600 million years would need to sit inside a dark matter halo of very roughly 1 trillion solar masses if it were converting gas at anything like a normal rate. Halos that massive are not merely rare at that epoch. According to the measured statistics of primordial density fluctuations, they should essentially not exist yet. There has not been enough time for that much material to have collected in one place. And if you insist on putting the galaxy in a halo that could plausibly exist at that epoch, then to reach the observed stellar mass, the galaxy must have converted more than 100% of the ordinary matter available to it into stars. More than all of it, more than everything it had. That is not an efficiency problem. That is a bucket holding more water than you poured into it. That single sentence is the reason for the cream circle. It is the reason an astronomer sat alone in a dark room, not quite believing a number on a screen. It is the reason 6 red smudges have since generated thousands of pages of papers, several genuinely bad-tempered conference sessions, and a low persistent discomfort in extragalactic astronomy that has not gone away as more data has arrived. But there is something we have skipped over, and it is not a small thing. Every number I have just given you depends on knowing how far away these objects are. The mass estimate depends on the distance. The age of the universe at the moment of emission depends on the distance. The entire impossibility depends on the distance. And nobody measured that distance with a ruler. Nobody could. So how do you know, from a red smear a few pixels across, that you are looking at something 13 billion years in the past? Light takes time. That is the simplest sentence in astronomy, and almost everything else in the field is a consequence of it. When you look at the moon, you are seeing it as it was about 1¼ seconds ago. The sun is 8 minutes and 20 seconds in the past. Proxima Centauri, the nearest star beyond our own, is 4.24 light-years away, which means the light arriving from it tonight left before a good many things in your life happened. Step outside on a clear night, and every point of light above you is a separate historical document with a separate publication date, all of them being read simultaneously by your eye, none of them current. The Webb telescope was built to push that principle as far as physics allows, not to see far away, exactly, to see long ago, to collect light that departed its source so long before the Earth existed that the source itself may no longer be anything like what the image shows. But knowing that light is old does not tell you how old. For that you need a clock, and the clock came from a discovery made in stages by several people who did not entirely agree about what they had found. The first stage belonged to Vesto Slipher, working at the Lowell Observatory in Arizona in the years around 1912. Slipher was doing something painfully slow. He was taking spectra of what were then called spiral nebulae, faint smudges whose nature was completely unresolved. Nobody knew whether they were nearby clouds of gas inside our own galaxy or separate galaxies at enormous distance. To take a spectrum of one, Slipher had to hold a photographic plate under a faint smear of light for 20, 30, 40 hours across multiple nights, guiding the telescope by hand. What he found in those spectra was that the absorption lines of familiar elements were not where they should be. They were shifted, and in almost every case, they were shifted toward the red end of the spectrum, which meant the object was moving away. By 1917, he had measured about 24 of them, and most were receding at hundreds of kilometers per second. Nobody knew what to do with that. The second stage belonged to Henrietta Leavitt, who had been employed at the Harvard College Observatory to measure the brightness of stars on photographic plates. Studying variable stars in the Magellanic Clouds, she noticed that a particular class of them, the Cepheids, pulsed with a period that tracked their intrinsic brightness. A Cepheid that took 30 days to complete a cycle was genuinely more luminous than one that took 3, which meant that if you could find a Cepheid in a distant object and time its pulse, you knew how bright it really was, and comparing that to how bright it appeared gave you the distance. She had built a ruler for the universe out of a pattern in a stack of glass plates. The third stage belonged to Edwin Hubble at the Mount Wilson Observatory in California, who put the two things together. Using Leavitt's method on Cepheids, he found in the Andromeda Nebula, he established in the mid-1920s that Andromeda was not inside our galaxy at all, but a separate system at vast distance. The spiral nebulae were other galaxies. Then, in 1929, he combined his distances with Slipher's redshifts and published the relation that carries his name. The further away a galaxy is, the faster it recedes, and the relationship is roughly proportional. The Belgian priest and physicist Georges Lemaitre had derived the same expanding solution from general relativity 2 years earlier and had even estimated the expansion rate, but he published in a small Belgian journal in French, and almost nobody read it. What all of them had found, in pieces, is that space itself is stretching. Galaxies are not flying outward through space, like debris from an explosion. The space between them is getting larger, and light travelling through that space gets stretched along with it. That stretch is the clock. The measure of the stretch is called redshift, and astronomers write it as the letter Z. It is defined simply. A redshift of 0 means the light arrives with exactly the wavelength it left with. No stretching, no travel time, worth mentioning. A redshift of 1 means the wavelengths have doubled, which means the universe has doubled in size since that light was emitted. A redshift of 8 means the wavelengths have been stretched by a factor of 9, and the universe was 1/9 the size it is now. Redshift is not a speed, it is a ratio of scale between then and now. To convert that ratio into a number of years, you need to know the expansion history, and that is where the standard model earns its keep. We know the current expansion rate to within a few percent. We know the proportions of the ingredients, roughly 5% ordinary matter, about 27% dark matter. The remaining 68% dark energy, from a combination of the cosmic microwave background, the clustering of galaxies, and supernova surveys. Feed those into the equations of general relativity, and the whole timeline unfolds. At a redshift of 8, the universe was about 650 million years old. At 10, roughly 480 million. At 13, around 330 million. At the highest confirmed redshifts we have reached so far, above 14, the universe was under 300 million years old, about 2% of its present age. These are not soft numbers. The cosmic microwave background, the relic glow released 380,000 years after the Big Bang, when the universe first cooled enough for atoms to hold together, has been mapped to extraordinary precision, most recently by the Planck satellite. It gives us a snapshot of the infant universe's composition and geometry that constrains everything downstream. There is one honest wrinkle here, and it is worth naming because it will come back. The current expansion rate does not agree with itself. Measure it from the cosmic microwave background, working forward through the model, and you get about 67 kilometers per second per megaparsec. Measure it locally, using Cepheids and supernovae in nearby galaxies, and you get closer to 73. Both measurements have shrunk their error bars over the past decade, and instead of converging, they have separated. That disagreement has a name, the Hubble tension, and nobody has resolved it. It does not change the broad timeline, but it is a standing reminder that the framework we are about to test against 6 red smudges is not itself perfectly clean. Now, how do you get a redshift out of an image rather than a spectrum? You cannot see the spectral lines in a photograph, but you can see something almost as good, and it comes from the most abundant substance in the universe. Neutral hydrogen gas absorbs ultraviolet light below a particular wavelength with brutal efficiency. Any photon energetic enough to knock an electron up from the ground state in a hydrogen atom gets swallowed. In the early universe, before the gas between galaxies was fully ionized, space was thick with neutral hydrogen. so light from a distant galaxy at wavelengths shorter than that threshold simply does not make it to us. It is absorbed somewhere along the way. The consequence is a cliff in the spectrum. Above the threshold wavelength, the galaxy shines. Below it, nothing. And because the whole spectrum is stretched by redshift, that cliff moves to longer wavelengths the further away the object is. So you photograph the same patch of sky through a series of filters, each sampling a different band. A distant galaxy will be invisible in the shorter wavelength filters, appear abruptly in one particular filter, and remain visible in all the longer ones. Astronomers call it a dropout. Find which filter the object drops out of, and you have bracketed its redshift without ever taking a spectrum. Combine that with the colors in the remaining filters and you get a photometric redshift, a distance estimate built entirely out of brightness measurements. It is fast, it works on faint objects that are far too dim for spectroscopy, and it is how essentially every high redshift candidate is first identified. It is also, as we will see, capable of being badly wrong. Sit with the geometry of it for a moment. The light from one of these galaxies left when the universe was around 1/20th of its current age. It has been in transit ever since, crossing space that was expanding underneath it the whole way, so that the distance it had to cover kept growing while it travelled. It passed through the era when the first stars ionized the intergalactic gas. It passed the formation of our own galaxy's oldest stars. It passed the collapse of the cloud that became the sun, the accretion of the Earth, the entire fossil record. It was still in flight when the last dinosaurs died, and still in flight when the first grass appeared, and still in flight through every year of recorded human history. And in the final second of that journey, it struck a gold-coated beryllium mirror 6.5 meters across, floating in the dark 1,000,000 miles from the planet where it was assembled, and was converted into a number. That is what the astronomer was looking at, not a picture of a galaxy, a timestamp. Which brings us to the harder half of the problem. Understanding that the clock exists is one thing. Building a machine that can actually read it, and getting that machine to a place where it can work, took 30 years, nearly ended in a Congressional Appropriations Committee, and depended on 344 separate mechanisms firing perfectly, with nobody within 1,000,000 miles to fix them. That story begins on Christmas morning. The Ariane 5 rocket stood on the pad at the Guyana Space Center on the northeastern coast of South America, the equatorial jungle steaming around it in the morning heat, a white tower against a grey sky. It was Christmas Day, 2021. Inside the fairing, folded down into a volume not much larger than a delivery van, was the most expensive scientific instrument ever built and flown. On the ground, controllers worked through a countdown they had rehearsed hundreds of times. Some of the engineers watching had been employed on this machine for more than 20 years. A few had gone grey during its construction. A few had retired and been brought back as consultants because they were the only people who still understood a particular subsystem. They all knew the number, 344. 344 single-point failures. That was the count of mechanisms that had to work perfectly, in sequence, with no redundancy and no possibility of repair. The telescope was going to a gravitational balance point 1,000,000 miles from Earth, roughly 4 times the distance of the Moon. No astronaut could reach it, no servicing mission existed, or could realistically be built. If any one of those 344 actions failed, the entire observatory, 25 years of design, $10 billion of public money, and the working lives of several thousand people would become an exquisite piece of inert debris in a slow orbit around the sunday. The list of what had to work was not abstract. The covers over the sunshield had to release 5 separate layers of a plastic film called Kapton, each about as thick as a human hair or thinner, each roughly the size of a tennis court, had to unfold from their stowed pallets without snagging. 90 individual cables running through dozens of pulleys had to draw those layers taut and hold them apart. The secondary mirror had to swing out on a tripod of hinged struts and lock into position within a fraction of a millimeter. The 2 side wings of the primary mirror, folded back to fit inside the rocket, had to rotate into place and latch. A cryocooler had to start and run continuously to chill the mid-infrared instrument to about 7 degrees above absolute zero, which is colder than anything the telescope could reach passively, even in permanent shade. In testing, some of these things had not worked. during a sunshield deployment test in 2018, the membrane snagged and tore. During an acoustic test simulating the vibration of launch, fasteners came loose and had to be hunted down inside the structure. Each incident cost months. The schedule absorbed the delays. The count of things that could go fatally wrong did not go down. The project had begun in 1996 under a different name, the Next Generation Space Telescope, with a projected cost of around $500 million and a launch date of 2007. Over the following 15 years, the cost estimate grew by a factor of 20, and the launch date receded by 14 years. In 2011, a subcommittee of the United States House of Representatives voted to terminate the program outright. The reasoning was not unreasonable. A project consuming a growing share of the entire astrophysics budget, with a history of overruns, was crowding out every other mission in the queue. The reversal came through a combination of scientific lobbying, institutional pressure, and the awkward fact that the European Space Agency and the Canadian Space Agency had already committed hardware and could not simply be told the arrangement was cancelled. Europe was providing the launch vehicle and 2 instruments. Canada was providing the fine guidance sensor, without which the telescope could not point steadily enough to observe anything at all. The program survived, but everyone who worked on it afterwards understood the terms. There would not be a second reprieve. The telescope that eventually left the clean room in Redondo Beach, California, and travelled by ship through the Panama Canal to French Guiana, he was a considerably more ambitious object than the one proposed in 1996. Its primary mirror was 6.5 meters across, made of 18 hexagonal segments of beryllium, each polished and then coated with a layer of gold about 1,000 atoms thick. Beryllium was chosen because it holds its shape at cryogenic temperatures rather than shrinking unpredictably. Gold was chosen because it reflects infrared light with better than 98% efficiency. The total amount of gold on the mirror is roughly the mass of a golf ball. The sun shield, once deployed, would hold the cold side of the observatory at around -233 degrees Celsius, while the sun-facing side sat above 80 degrees. The temperature difference across 5 thin sheets of plastic was greater than the difference between a summer afternoon on Earth and the surface of Mars. That gradient is not a design flourish, it is the entire point. An infrared telescope that is warm sees nothing but itself. Every part of the optical path had to be colder than the faint ancient heat it was trying to detect. The launch lasted less than half an hour, and the Ariane 5 performed what the mission planners afterwards described with unusual candor as a perfect insertion. The telescope separated from the upper stage, unfolded its solar array within minutes, and began a 30-day cruise toward the second Lagrange point, a gravitational saddle in the Earth-Sun system where a spacecraft can hold station with only occasional small corrections. The precision of that insertion had an immediate and enormous consequence. The rocket had placed the observatory so accurately that the telescope needed far less of its own propellant for course corrections than had been budgeted. That saved propellant is the mission's clock, because station-keeping fuel is the one consumable that cannot be replaced. The planned 5 to 10 years of operation became something closer to 20. In its first hours in flight, before it had taken a single photon of scientific data, the mission's lifetime roughly doubled. Then the unfolding began. The deployment sequence started about 12 hours after launch and ran for 2 weeks. The operations team at the Space Telescope Science Institute in Baltimore worked in shifts around the clock, watching telemetry, confirming each motor current and each latch signal before authorizing the next step. It was deliberately, almost painfully slow. Several steps that could have been executed in minutes were spread over days so that engineers could examine temperatures and replan if anything looked marginal. At one point, the team paused the entire sequence for a day, simply to let the solar array settle into a better power configuration. The sunshield covers rolled back. The pallets holding the folded membranes swung down, forward and aft. Then the layers themselves were drawn out and tensioned, one at a time, each separated from its neighbours, so that heat could radiate out through the gaps at the edges, rather than conducting straight through. If a single layer had caught on a rivet or torn under tension, the thermal design would have been compromised, and the instruments would never have reached the temperature at which they could work. The layers deployed, they held. Next came the secondary mirror, a small convex disc of beryllium mounted on 3 struts. Its alignment tolerance was measured in fractions of a millimeter, because everything the primary mirror collects must bounce off this one small surface before reaching the instruments. The struts swung outward, the latches engaged, the mirror locked. Then the two wings of the primary, each carrying 3 of the 18 segments, folded back during launch. On the 12th and 13th days, they rotated into position and latched. The full mirror, the largest ever flown, was in one piece. On the 14th day, the deployment was declared complete. 344 single-point failures had not failed. The work was not over. Over the following months, each of the 18 segments was moved into alignment using actuators mounted on its back, in steps measured in nanometers, until the 18 separate reflections of a single star converged into one point. The instruments were calibrated against known sources. In the spring of 2022, the first properly focused test images arrived, and they were sharp enough that the optics team knew, before any science had been done at all, that the telescope was going to beat its own specification. There is a human dimension to this that is easy to skip past. For the astronomers who would use the machine, the waiting had not been 2 weeks or 30 days. Many had written doctoral theses on science this telescope would do, on the assumption that it would fly before they graduated. They had defended those theses, taken postdoctoral positions, moved countries, been awarded tenure, and watched the launch dates slip year after year after year. Some of the people who had designed instruments for it did not live to see it launch. The ones who remained had spent decades preparing to answer a question they had never been able to touch. And the question was concrete, and it was old, and everyone thought they knew roughly what the answer would look like. What was actually out there, in the first few 100 million years? For decades, the answer had been clear. The early universe was a nursery, and the things in it should be small. That expectation was not a hunch. It was the output of a chain of physical reasoning that had been checked against observation at every link, and it is worth walking that chain slowly, because the strength of the expectation is what makes the surprise a surprise. If the models had been vague, 6 massive galaxies would have been a curiosity. The models were not vague. Start at the beginning, with the cosmic microwave background. When we map that relic radiation, we find it is almost perfectly uniform in temperature across the whole sky, but not quite. There are ripples, variations of about 1 part in 100,000, hotter and colder patches on every angular scale. Those ripples are the fossil imprint of density variations in the matter of the early universe, and their statistical pattern, how much variation exists on each spatial scale, is called the primordial power spectrum. It has been measured with high precision. From that power spectrum you can calculate, without any free parameters worth mentioning, how many dark matter halos of any given mass should have collapsed by any given time. This calculation has a long history, going back to work by William Press and Paul Schechter in the 1970s and refined many times since. It produces what is called the halo mass function, and it has a distinctive shape. There are enormous numbers of small halos and a steeply falling number of large ones, and at early times, the fall-off at the massive end is not gentle. It is exponential. That exponential is the ceiling. It says that at a redshift of 8, halos of 100 billion solar masses exist but are uncommon. Halos of 1 trillion solar masses are so rare that in the small patch of sky a survey can cover, you should expect essentially none. Not few, none. The second link in the chain concerns what happens to ordinary matter inside those halos. Gas falls in, but falling in is not the same as forming stars. To form stars, gas must cool, and cooling requires a mechanism to radiate energy away. In the modern universe, that job is done largely by heavy elements, carbon and oxygen and iron, which have many available energy levels and are extremely efficient radiators. In the early universe, those elements did not exist yet. The only coolants available were hydrogen and helium, and molecular hydrogen in particular, which is fragile and easily destroyed by ultraviolet light from the very first stars. So the first structures had to fight to cool at all, and once the first stars did ignite, they made the problem worse before they made it better. Massive stars produce torrents of ultraviolet radiation and then explode, and both the radiation and the explosions inject energy into the surrounding gas, heating it and pushing it outward. In a small halo with weak gravity, A single generation of supernovae can expel most of the remaining gas entirely. The galaxy shuts down, sometimes for tens of millions of years, until the gas cools and falls back. This is called feedback, and it is the single most important reason that galaxies are as inefficient as they are. Left to gravity alone, essentially all the gas in a halo would collapse and turn into stars very quickly. The universe would have burned through its hydrogen long ago. Feedback is why that did not happen. The third link is that all of this had been simulated, at great expense, by several independent groups. Through the 2010s, large cosmological simulations became the field's main theoretical instrument. Projects with names like Illustris, Eagle, and Fire ran the physics forward from initial conditions drawn from the measured power spectrum following gas, stars, and feedback in millions of galaxies at once. They were tuned to reproduce the present-day universe, and they did so remarkably well. Galaxy sizes, the distribution of galaxy masses, the relationship between a galaxy and its central black hole, the pattern of clustering on large scales, all of it came out roughly right. Run those simulations back to a redshift of 7 or 8, and they agreed with each other. The most massive galaxies at that epoch should hold at most a few billion solar masses in stars, and objects even that large should be rare enough that you would have to search a wide area to find one. The typical galaxy at that time was expected to hold 10 million to a few 100 million solar masses. Not 10 billion, certainly not 100 billion. The fourth link was observational, and it came from people who had spent their careers proving that the theory held. Through the 2000s and the 2010s, a relatively small community pushed the Hubble Space Telescope to its physical limit, hunting the most distant galaxies. Garth Illingworth at the University of California, Santa Cruz, was one of the architects of that effort. Richard Bowens at Leiden Observatory and Pascal Oesch, first at Yale and later at the University of Geneva, were among the people who did the painstaking work of building catalogues from images that had taken hundreds of hours to accumulate. The Hubble Ultra Deep Field, assembled in 2003 and 2004, remains one of the most productive photographs ever taken. It covered a patch of sky roughly the size of a grain of sand, held at arm's length, and it contained about 10,000 galaxies. Later campaigns went deeper still. Working through those images, the teams found galaxies at redshift 9, at redshift 10, and eventually a single tentative candidate at redshift 11, an object called GNZ11, which held the distance record for years. And every one of those galaxies behaved. They were faint. They were compact, often only a few hundred parsecs across. Their inferred stellar masses were comfortably under 1 billion suns, in most cases far under. The bright end of the population at high redshift was empty, exactly as the exponential cutoff in the halo mass function said it should be. The great spirals and ellipticals assembled later, during the era astronomers call cosmic noon, around redshift 2, when the star formation rate of the whole universe reached its maximum and then began its long decline. The story was coherent. Theory predicted small early galaxies. Simulations produced small early galaxies. Observations, pushed to the very edge of what was technically possible, found small early galaxies. 3 independent lines agreeing is the strongest kind of scientific comfort there is. So when the Webb telescope was being designed, the science case was written around extending that agreement. The infrared sensitivity was specified in order to reach the epoch between redshift 10 and 15, the first few 100 million years, where Hubble simply could not go because the relevant light had been stretched clean out of its detector's range. The purpose, stated in proposal after proposal, in review after review, in every public lecture given to justify the cost, was to find the first small galaxies, the first assemblies of matter that deserved the name at all. That sentence appeared in almost every document the program produced across 25 years, built to find the first small galaxies. The problem, which surfaced within weeks of first light, is that it found galaxies that were not small. And that expectation of smallness was not a soft prediction that could be quietly adjusted. It was woven into the same model that had successfully explained the ripples in the microwave background, the abundance of deuterium and helium produced in the first minutes, the way galaxies cluster across billions of light years, and the accelerating expansion measured with distant supernovae. That model has been tested against wildly different kinds of data for 30 years and has come through every time. To contradict it at the exact epoch the telescope had been designed to examine was not going to be a small correction to a footnote. The images had been taken, the photons had been counted, and the numbers coming out of the pipeline in Baltimore in the summer of 2022 said that 6 of the objects in one ordinary strip of northern sky were giants. The data landed on the servers at the Space Telescope Science Institute in Baltimore in the early summer of 2022, and it did not look like the pictures the public would see a few weeks later. Those were processed, color-balanced, chosen for composition. What arrived first were raw frames from the near-infrared camera, full of cosmic ray hits and detector artifacts, each one a monochrome field of noise, with points of light buried in it. A typical observing run produced thousands of exposures. The camera imaged through a set of filters spanning wavelengths from about 1 micrometer out to nearly 5, which meant every object in the field was measured multiple times in multiple bands. Those measurements are the raw material for everything that followed. The filters act like extremely coarse prisms. They cannot resolve a spectral line, but they can tell you roughly how much energy an object is emitting in each stretch of the infrared, and from that shape you can estimate both how far away it is and what kind of stars are producing the light. The survey team ran the frames through a pipeline. Cosmic rays were removed. Individual exposures were aligned and stacked. Sources were detected, catalogued, measured through each filter, and assigned preliminary photometric redshifts and stellar masses. In the first weeks, the pipeline was producing candidates steadily, and most of them behaved exactly as the previous section would lead you to expect. Small, faint, irregular, low mass. But a handful came out wrong. They were too bright for their apparent distance. Their colours were too red. The dropout pattern placed them above redshift 7, and at that distance, an object that bright had to be either enormous or something other than a galaxy. Ivo Labbé had been working on high redshift galaxy detection for most of his career, with a specific interest in finding the most massive early systems, which meant he had spent years being the person who checked whether other people's massive early systems were real. He knew every way this measurement fails. His first reaction was suspicion, and he had a specific suspect in mind. The photometric method has a well-documented failure mode. Dust reddens light. A galaxy at redshift 2 or 3, full of dust, can produce colours that look very similar to a pristine galaxy at redshift 8, because in both cases the blue end of the spectrum is suppressed and the red end is not. One is dimmed by dust in its own interior. The other is dimmed by neutral hydrogen across billions of light years. The filters cannot easily tell the difference. So the team spent weeks trying to make the galaxies into dusty nearby imposters. They varied the dust content and the dust geometry. They tried older stellar populations, which are redder, and younger ones with heavy obscuration. They allowed for a contribution of light from an accreting black hole. They ran alternative fitting codes with different underlying stellar libraries and different assumptions about how star formation had proceeded over time. Under each set of assumptions, the fit to the data came back preferring the distant solution. And under each set of assumptions, the implied stellar mass stayed enormous. There were 6 of them, sitting in a patch of sky small enough that you could cover it with a fingernail at arm's length, with photometric redshifts between roughly 7.5 and 9. If those redshifts were right, the universe was between 500 and 700 million years old when the light left. The masses ran from around 10 billion solar masses at the low end, up to about 100 billion at the high end. To be clear about what that means, the higher figure is not merely large for its epoch, it is large full stop. It is comparable to the entire stellar content of the Milky Way, a galaxy that has been assembling continuously since a few 100 million years after the Big Bang, and has swallowed a long list of smaller companions along the way. Labbé and his colleagues did not rush to publish. They understood the claim would be incendiary, and that the burden would fall on them. They brought in Joel Leisure at Penn State, who had developed an independent fitting code with a reputation for being conservative. It tended to return lower masses than competing methods, because it allowed for more complicated star formation histories, and therefore did not assume that all the light had to come from a single recent burst. Leisure ran the 6 objects through his own machinery, expecting to shave the numbers down. They came back high, not identical but high enough that the problem did not go away, and high enough that the 2 independent analyses agreed on the thing that mattered. These were not artifacts. They were not misidentified foreground objects. They were galaxies, they were where the colours said they were, and they were heavy. Leger later described the experience to an interviewer with an analogy that spread through the field faster than any of the technical results. It was, he said, like walking into a nursery expecting to find babies and finding a fully grown adult standing among the cots. He also used a blunter phrase in conversation, one that ended up in headlines. He called them universe breakers. The remark was not scripted, and it is not a rigorous statement, but it captured something that a page of equations could not, which is the particular quality of the wrongness. The problem was not that the objects were unfamiliar. The problem was that they were completely familiar and in the wrong place. A galaxy the size of the Milky Way is not exotic. We live in one. It is just not supposed to be finished when the universe is 5% of its current age. The paper went to the journal Nature in late 2022 and appeared in February of 2023 under a title that made no attempt to soften anything. A population of red candidate massive galaxies about 600 million years after the Big Bang. The word candidate is doing important work in that title, and the authors meant it, but the abstract stated plainly that if the masses were correct, these objects were more massive than any model could produce at that epoch, and that this constituted a direct challenge to the standard cosmology. The response was immediate and it was loud. Within days, the paper was being argued about at conferences, in seminar rooms, on social media, and in rapid response papers posted to the preprint server. There were broadly two reactions, and the split was roughly along the line between theorists and observers, though not neatly. One camp was exhilarated. Cosmology had been quiet for a long time. The standard model had absorbed every challenge thrown at it for 3 decades, which is intellectually satisfying and professionally rather dull. A genuine anomaly, in fresh data, from an instrument that had just come online, is the kind of thing that makes careers and rearranges research programs. The other camp was skeptical, and their skepticism had a precise target. The masses were photometric. They were not measured, they were fitted, and they were fitted using models calibrated on galaxies in the nearby universe. Every step in that chain carried an assumption. How many low-mass stars accompany each massive one? Whether star formation was smooth or came in bursts? How much dust there was and how it was arranged? Whether any of the light came from a black hole rather than from stars? Get any of those wrong, and the mass comes out wrong, potentially by a large factor. Both camps agreed on one thing, and it turned out to be the durable part. Something was there that had not been predicted. The Webb telescope had not simply pushed the known galaxy population a little further back along a curve everyone had already drawn, it had found objects that did not sit on the curve at all, and within the same images, scattered among the same fields, there was already a second population that nobody had a name for yet. They were not extended smudges. They were points, tiny, saturated, and so red that in the shorter filters they barely registered as anything at all. Erica Nelson is an astronomer at the University of Colorado Boulder, and in the autumn of 2022 she was doing the unglamorous work that follows any new dataset, going through a catalogue object by object, looking at cutouts, deciding what each thing was. Most of it was routine. Then she kept running into a class of object that would not classify. They were tiny. In the near-infrared camera images, they occupied only a few pixels, which at that resolution means they were unresolved or barely resolved. A normal galaxy at that distance, even a compact one, has some visible extent. These did not. They looked like stars. But they could not be stars because they were the wrong colour. In the longest wavelength filters, they blazed a deep saturated red. In the shorter filters, they nearly vanished. No star in our own galaxy produces that combination. The colours place them at high redshift, and an unresolved point source at high redshift is a strange thing to be, because it means all that light is coming from a region smaller than the telescope can separate. She began describing them informally, in the way people do when a category does not exist yet, as the little red dots. The phrase was not coined in a paper or assigned by a committee. It circulated in conversations and slide decks and hallway arguments, and within a year, it had become standard usage in the literature. There are now papers with the words "little red dots" in the title, capital letters and all, which is an unusual fate for a nickname that started as shorthand. Once people started looking for them deliberately, They turned up everywhere. Every deep field had them. They were not a peculiarity of one survey or one instrument configuration. Estimates of their abundance settled at something like 1 or 2% of the galaxy population at these redshifts, which sounds small until you remember that they are, by a factor of many, more common at redshift 6 than anything resembling them is in the universe today. They cluster in cosmic time. They appear at around redshift 8 or 9, become most common somewhere between redshift 7 and 4, and then largely disappear. Whatever they are a phase, and the universe has stopped doing it. The physical size implied by their compactness is startling. Correcting for the telescope's resolution, the upper limits on their extent are of order a few hundred light-years across, and in the best constrained cases considerably less. A few hundred light-years is roughly the size of a large globular cluster, one of the dense spherical swarms of old stars that orbit our own galaxy. A globular cluster contains a few 100,000 to a few million stars, and is, on a galactic scale, a rounding error. These objects emit as much light as an entire galaxy from a volume that small. When astronomers assembled their spectral energy distributions from the filter measurements, a distinctive shape emerged, and it was unlike anything in the standard templates. Plotted appropriately, the shape has a steep decline in the blue, a bend, and then a flat or rising continuum toward the red. The literature settled on calling it a V-shape. In some objects, there was also a clear excess at the longest wavelengths, consistent with dust heated to high temperatures. That shape is a problem, because it looks like two different things stitched together. The blue portion looks like unobscured starlight, or an unobscured accretion disk. The red portion looks like heavily obscured emission. Getting both in the same object, at the same time, requires either an unusual geometry or two separate components. In the nearby universe, a compact source with a rising red continuum and hot dust has a standard identification. It is an active galactic nucleus, a supermassive black hole at the center of a galaxy, pulling in gas that spirals inward through a disk, heating by friction and compression until the inner regions reach hundreds of thousands of degrees and radiate ferociously, surrounded by a thick torus of dust and gas that absorbs some of that radiation and re-emits it in the infrared. If the little red dots were active nuclei, the compactness resolved itself immediately. The light would be coming from a region a fraction of a light-year across, not from a spread-out population of stars. Of course it would look like a point, but that identification carried a cost, and the cost was severe. For a black hole to power a source that bright at redshift 7, it would need a mass in the range of 10 million to 100 million times the mass of the Sunday already, within the first 600 to 800 million years of cosmic history. For scale, the black hole at the center of our own galaxy, Sagittarius A star, is about 4 million solar masses, and it has had the full 13 billion years to accumulate that. The objects implied here were 10 to 25 times heavier in less than a 15th of the time. The alternative interpretation was that these were not black holes at all, but extraordinarily compact starbursts. Stars packed so densely that the combined light of millions of them mimicked a point source. That would keep the black hole problem at bay, but it created a different one. To produce that much light from stars alone, in a volume that small, you need a stellar density far beyond anything observed anywhere in the local universe. And you need the whole thing to be stable enough to exist, rather than immediately tearing itself apart or turning into one enormous merged object. Neither answer was comfortable, and photometry could not decide between them. Broadband filters measure how much light arrives in a wide chunk of the spectrum. They cannot see the individual emission lines that would settle the question, because the lines are narrow and the filters are wide, and a strong line simply raises the measured brightness of the whole band by a modest amount that is easily confused with a change in the continuum. What the field needed was a spectrum, not a smear of colours, but the light spread out finely enough that individual atomic transitions become visible as discrete features, with measurable positions and measurable widths. The Webb telescope carried an instrument for exactly that, and getting it to work on objects this faint had been one of the hardest requirements in the entire design. A camera gives you a photograph, a spectrograph gives you a fingerprint. The near-infrared spectrograph aboard the Webb telescope is, mechanically, one of the strangest instruments ever flown. Its central component is a micro-shutter array, a grid of about 250,000 individual shutters, each roughly the width of a human hair, each capable of being opened or closed independently. To take spectra of 100 faint objects scattered across a crowded field, you open the 100 shutters that sit over those objects and close everything else. Without that, light from neighbouring sources would overlap and contaminate every spectrum on the detector. The shutters are opened by sweeping a magnet across the array and then held open electrostatically. It is a delicate arrangement. It had never been flown before, and the mechanism that drives it was on the list of 344 things that had to work. It worked. Through the winter and spring of 2023, the spectrographs went to work on the candidates that the imaging surveys had turned up, and the results began to reshape the conversation almost at once. The largest single effort was a program called the Advanced Deep Extragalactic Survey, a joint undertaking between the camera and spectrograph instrument teams using their guaranteed observing time. It targeted a field in the southern sky that had, like the extended growth strip, already been examined exhaustively by Hubble. The team included many of the same people who had built the pre-Webb picture: Pascal Ush, Garth Illingworth, Richard Bowens, Roberto Maialino at Cambridge, Daniel Eisenstein at Harvard, and a long list of others. This matters for how the results were received. These were not insurgents looking to overturn cosmology. They were the people whose careers had been spent establishing that early galaxies were small, using the previous telescope, and they were cautious by temperament. Their stated approach was methodical and slightly unglamorous. Take spectra, confirm redshifts. Only then, interpret. The first thing the spectra did was kill some of the excitement, and this is the part of the story that gets less attention than it deserves. A number of the most spectacular early candidates simply evaporated. The most famous casualty had been flagged in the first weeks of data as a possible galaxy at redshift 16, which would have made it by a wide margin the most distant object ever identified. It generated headlines. It generated papers. When the spectrograph was pointed at it, the object turned out to sit at redshift 4.9, not 13 billion years in the past, but 12. Still a distant galaxy, not remotely the same thing. The failure mode was exactly the one people had warned about. A dusty galaxy with strong emission lines at moderate distance had produced a set of filter measurements that mimicked the dropout signature of an extremely distant one. The photometric fit had chosen the wrong solution. Another well-known candidate, nicknamed Maisie's Galaxy, after the daughter of the astronomer who found it, had been estimated photometrically at redshift 14. Spectroscopy brought it down to 11.4. That is still an extraordinary object, seen when the universe was around 400 million years old, and it survives as a genuine early galaxy, but it is not what it briefly appeared to be. And crucially, Maisie's Galaxy is small, low mass, compact, exactly the sort of thing the models predicted. Its downward revision was a useful public reminder that photometric redshifts are estimates with tails, and that the most extreme objects in any catalogue are the ones most likely to be the errors. There was one more casualty, and it was one of the original 6. When the spectrograph examined the reddest and one of the most extreme objects in the Labbé sample, it turned out to sit at redshift 5.6 rather than 8, and its light was dominated not by stars, but by an obscured accreting black hole buried in an enormous quantity of dust. It was a genuinely remarkable object in its own right. It was not a 100 billion solar mass galaxy in the first 600 million years, so the skeptics were partly vindicated, and they said so, but the population did not collapse. That is the crucial result, and it is why the problem is still with us. When the spectrograph was pointed at the surviving candidates from that sample, and at similar objects turned up by other surveys, most of them were confirmed at or near the redshifts the colours had indicated. They were not foreground imposters. They were where they appeared to be in the universe's first 700 million years. And when masses were re-derived using the far better constraints that a spectrum provides, they came down, but not nearly enough. The typical downward revision was a factor of 2 or 3. A candidate estimated at 100 billion solar masses might settle at 30 or 40 billion. To reconcile these objects with the pre-Webb models, you would have needed a factor of 10 or more, applied consistently to every object. A 40 billion solar mass galaxy at 600 million years is a smaller impossibility than a 100 billion solar mass one. It is still an impossibility, The same survey produced a result that framed the problem more sharply, almost by accident. In the same deep field, at the very limit of sensitivity, the team spectroscopically confirmed a galaxy at redshift 13.2, which at the time was the most distant such confirmation ever made. That record has since fallen more than once. A galaxy at redshift 14.3 was confirmed the following year, and by 2025 the record had been pushed past 14.4, with the universe under 300 million years old. And every one of those record holders is small, a few tens of millions to a few hundred million solar masses in stars, light-dominated by young, hot, metal-poor stars. Exactly what a protogalaxy is supposed to look like. This is the shape of the problem, stated as precisely as I can manage. It is not that the early universe failed to produce the small galaxies we predicted. It produced them. They are there, at the highest redshifts we can reach, behaving themselves. The problem is that alongside them, at slightly later times, sit objects that appear to have run through the entire growth sequence at a speed the models cannot reproduce. The early universe did not do one unexpected thing. It did a much wider range of things than we allowed for. Meanwhile, the spectrographs were being pointed at the little red dots, and here the results were unambiguous in a way that the galaxy masses never were. Several programs contributed. One used the enormous foreground galaxy cluster known as Pandora's cluster as a gravitational lens, exploiting the way a cluster's mass bends and magnifies the light of everything behind it to reach objects that would otherwise be far too faint. Another, led by Jorrit Matthee, then at the Institute of Science and Technology Austria, worked through a different sample. What came back were broad emission lines, specifically the Balmer lines of hydrogen, and particularly the transition astronomers call hydrogen alpha, appeared not as narrow spikes, but as wide humps, spread out across a range of wavelengths corresponding to gas moving at 1 to 2,000 kilometers per second along the line of sight. In the nearby universe, that feature has one standard interpretation, and it is not controversial. Narrow lines come from gas ionized across a large region, moving at ordinary galactic speeds. Broad lines come from a small region of gas very close to a massive compact object, orbiting fast enough that the Doppler shift smears the emission across a wide band. Broad hydrogen lines mean a black hole, and the width of the line combined with the luminosity gives you an estimate of its mass. The little red dots had them. Not all of them, but a large fraction, and in the best observed cases the signature was clean. So they host black holes. That part is settled. Everything after that part is not, because the same objects have refused to behave like active galactic nuclei in every other respect that has been tested. An accreting black hole, that bright, should be a strong X-ray source. When X-ray observatories were pointed at these objects, and when the data from many of them were stacked together to beat down the noise, almost nothing came back. A handful of individual detections exist. The population as a whole is far fainter in X-rays than its inferred accretion rate should allow. Accreting black holes also vary. The inner disk is small and turbulent, and its brightness fluctuates on timescales of days to months. Monitoring campaigns on these objects have found them remarkably steady. And then there is a feature that nobody expected at all. In several of the best spectra, the hydrogen lines show absorption as well as emission, and in some objects there is a pronounced break in the continuum of the kind normally produced by a dense population of stars of intermediate age. Both of those things are difficult to arrange around a bare accretion disk. By 2025, a genuinely strange proposal had gained traction. The suggestion is that these objects are black holes embedded in an envelope of dense gas so thick that the envelope itself develops a structure resembling a stellar atmosphere. Light from the accretion disk is absorbed, thermalized, and re-radiated by the surrounding cocoon, which then produces its own absorption features exactly as a star's photosphere does. The name that has attached to the idea is the black hole star. If that picture is right, then the mass estimates derived from the width of the emission lines may be substantially wrong, because the gas motions being measured are those of the envelope rather than of material orbiting close to the black hole. The objects would still contain black holes. The black holes might be considerably less massive than the first estimate suggested, which would ease one problem while creating others. Nobody knows yet. What is not in doubt is that a class of object was discovered, named, characterized, and shown to break at least 3 separate expectations within about 3 years. and that its interpretation is still moving, which leaves the harder question, underneath everything, if the masses are anywhere near right, and even after every downward revision they remain too high, then either our physics of galaxy formation is wrong in its details, or our cosmology is wrong in its foundations. Those are very different problems, and the field split over which one it was facing. The paper that turned an argument into a quantity came from Mike Boylan-Colchin at the University of Texas at Austin. Boylan-Colchin is not an observer. He is a theorist who works on galaxy formation and on the properties of dark matter, and he has a particular habit of taking an observational claim, holding it still, and asking what would have to be true elsewhere in physics for it to stand. In the spring of 2023, he published a short paper in Nature Astronomy with a title that told you exactly what it was going to do: stress testing the standard cosmological model with high redshift galaxy candidates. The argument runs in a straight line, and it uses almost nothing that is in dispute. Take a galaxy with a claimed stellar mass. Ask what dark matter halo it must sit inside. Stars are made from ordinary matter. Ordinary matter is about 16% of the total by mass, and no process can create it. So the halo mass has a floor, set by dividing the stellar mass by 16%, and then dividing again by whatever conversion efficiency you are willing to allow. Now ask how many halos of that mass should exist in the volume of sky the survey covered at the redshift in question. That number does not come from a simulation or a model of galaxy physics. It comes from the primordial power spectrum measured in the microwave background, propagated forward by gravity. It is about as close to a first principles prediction as cosmology offers. For the most extreme candidates, the answer was that the required halos should not exist, not that they should be rare, that the expected number in that patch of sky at that epoch was so far below 1 that finding several of them would be absurd. And if you refuse to invoke impossible halos, and instead put the galaxies inside the largest halos that plausibly could have formed, the required efficiency of converting gas into stars climbs from the few percent seen locally to 50%, to 80%, and for the most extreme objects past 100%. Past 100% is not an efficiency, it is a contradiction. It says the galaxy formed more stellar mass than there was material available to form it from. You cannot fix that by adjusting a feedback prescription or tuning a star formation law, because it is not a statement about astrophysics. It is a statement about conservation of matter. The paper was careful and it was explicitly conditional. Boylan-Colchin listed the ways out. The photometric masses might be overestimates. The redshifts might be wrong. Light from an accreting black hole might be inflating the brightness. He was not claiming the cosmology was broken. He was saying, precisely, that if the observations are taken at face value, then the cosmology is broken, and here is the arithmetic that connects those two statements. That was the contribution. Before that paper, the argument was about whether the objects were surprising. After it, the argument had a number attached, and everyone knew exactly what would have to be shown to make the tension go away. What followed was 2 years of people trying to show it. The counter-arguments came from many directions, but they shared a single premise. A stellar mass is not a measurement. It is the output of a model, and that model was calibrated on galaxies within a few 100 million light-years of here, in a universe already saturated with heavy elements, already dusty, already several billion years past the conditions being studied. There is no law requiring those calibrations to hold at redshift 8. The first and most consequential assumption is the initial mass function. When a cloud of gas collapses and fragments into stars, it does not produce stars of one size. It produces a spread, and in the local universe that spread has a remarkably consistent shape. Most stars are small, red dwarfs, a fraction of the Sun's mass, cool and faint and enormously long-lived, outnumber everything else by a wide margin. A small minority are massive, tens of solar masses, and those dominate the light output completely, because the luminosity of a star scales as something like the third or fourth power of its mass. A single star of 30 solar masses can outshine 1,000 stars of 1 solar mass. That distribution is called the initial mass function, and its shape controls the relationship between how much light a galaxy emits and how much stellar mass it contains. Assume the standard shape and a given brightness implies a given mass, because you're assuming a large, invisible population of dwarfs accompanying every bright star. But the universality of that shape is an empirical observation from the local universe, not a derived law. And there is good theoretical reason to think it should be different in the early universe. Fragmentation requires cooling. A collapsing cloud heats up as it contracts, and unless it can radiate that heat away, it stops fragmenting and forms fewer, larger objects. Heavy elements are efficient radiators. Pristine gas made only of hydrogen and helium is not. So the very first generation of stars, forming from gas that had never been enriched, is predicted by detailed simulations, notably work by Tom Abel, Volker Brom, and others going back to the late 1990s, to have been dramatically more massive than stars today, possibly hundreds of solar masses. If the galaxies the Webb telescope found were forming stars with a distribution tilted toward high masses, even partially, they would produce far more light per unit of stellar mass than a modern population. You would not need 100 billion suns to make that much light. You might need 20 or 10. This is not a correction for a measurement error. It is a statement that the conversion between light and mass, which the entire analysis rests on, may simply be different at that epoch. The second assumption is the shape of the star formation history. Standard fitting codes assume a reasonably smooth build-up of stars over time. If instead early galaxies formed stars in violent short bursts separated by quiet intervals, the light we see is dominated by whatever burst happens to be underway at the moment of observation. A galaxy caught mid-burst is extremely bright and extremely blue, and a code assuming smooth growth will attribute that brightness to a large, patiently assembled population that does not exist. The bursty picture is not an invention of convenience. Simulations with realistic supernova feedback have produced bursty star formation in small galaxies for years, because the physics forces it. Gas collapses, stars form, the most massive of them explode within a few million years, the explosions drive the remaining gas out, star formation stops, the gas cools and falls back, and the cycle repeats. Work on the star formation histories of nearby dwarf galaxies, including a long program led by Dan Weiss at Berkeley, using resolved stellar populations, had already shown that real small galaxies do exactly this. There is also a selection effect layered on top. If galaxies flicker, then any survey with a brightness limit preferentially catches them at their peaks. The bright end of the population you observe is not the bright end of the population that exists. It is the subset that happened to be flaring when the shutter was open. The third assumption concerns light that is not starlight at all. The little red dots demonstrated that accreting black holes were common and luminous in the early universe. If even 10 or 20% of the light attributed to stars in a massive candidate is actually coming from an accretion disk, the inferred stellar mass drops correspondingly. Roberto Maiolino and others have argued that this contamination may be widespread, and that fitting templates built on the assumption of purely stellar light are systematically biased at the highest redshifts. The fourth is dust, and dust is genuinely ambiguous. It absorbs blue light and re-emits in the infrared, so uncorrected dust makes a galaxy look fainter and redder than it is, which pushes mass estimates down. But an overestimated dust correction inflates the intrinsic brightness and pushes them up. Which direction the error runs depends on the geometry, and the geometry of dust in galaxies 600 million years old is not something anyone has observed directly. Andrea Ferrara and collaborators proposed a specific and testable version of this. In galaxies forming stars fast enough, radiation pressure can drive the dust out of the star-forming regions entirely, leaving the galaxy effectively transparent. Such a galaxy would appear unusually blue and unusually bright for its mass, which would explain part of the excess without requiring extra stars. And then there is the most direct proposal of all, which does not try to reduce the masses but tries to explain how they could be real. Avishai Dekel at the Hebrew University of Jerusalem and colleagues pointed out that the reason galaxies are inefficient is feedback, and that feedback takes time to operate. Supernovae do not explode until several million years after their stars form. If gas is dense enough, a star-forming cloud can convert a large fraction of itself into stars faster than the first supernovae can arrive to stop it. In the early universe, gas densities were far higher, because the whole universe was smaller and halos were more concentrated. Under those conditions, the argument runs, star formation could proceed essentially unregulated for its first few million years, reaching efficiencies of tens of % rather than a few. They called it feedback-free starburst formation. It requires no new physics. It requires only that the conditions were extreme enough that the usual brake had not yet engaged. Each of these effects, on its own, moves the numbers by a factor of 2 or 3. Taken together, they can plausibly bring the observations into contact with the standard model without touching cosmology at all. The objection to that, raised repeatedly and not unfairly, is that they all have to work simultaneously in the same direction on every object. When a model requires 4 independent corrections all pushing the same way to survive, the pattern has a name in the history of science, and the name is not flattering. None of those corrections does anything at all for the black holes. You can change the initial mass function, invoke bursty star formation, subtract accretion light, and rearrange the dust. And at the end of it, you still have to explain how an object of tens of millions of solar masses exists 600 million years after there was nothing. Black holes grow by swallowing matter, and swallowing matter is limited by a physical ceiling that is not a modelling choice. The ceiling is called the Eddington limit, and the logic behind it is almost embarrassingly simple. Gas falling toward a black hole heats as it compresses and radiates ferociously. That radiation streams outward and exerts pressure on the gas still falling in. At some accretion rate, the outward push of the radiation balances the inward pull of gravity, and further infall stops. The black hole has, in effect, blown away its own food supply. That limit scales with the black hole's mass, which means a growing black hole is allowed to eat faster as it gets bigger, and the result is exponential growth with a characteristic doubling time. For a plausible efficiency, that doubling time is roughly 45 million years. It is sometimes called the salpeter time, after Edwin Salpeter, who worked it out in the 1960s. Now run the sum generously. Take a seed black hole of 30 solar masses, the plausible remnant of one of the first massive stars. Let it form very early, and let it accrete at the absolute maximum permitted rate, continuously, without interruption, for 600 million years. That is about 13 doublings. 30 solar masses becomes a few 100,000. To reach 100 million, you would need another 8 or 9 doublings on top of that, which is another 400 million years you do not have. And the assumption of continuous maximum accretion is not merely optimistic, it is unphysical. Real black holes in the local universe are quiet almost all the time. Estimates of the fraction of its life a supermassive black hole spends actively accreting run from a few percent to perhaps 10. Between meals it sits idle, sometimes for hundreds of millions of years. The Milky Way's own black hole is currently accreting at something like 1 part in 100 million of its Eddington rate. It is, by any reasonable standard, starving. So the numbers coming out of the early universe demand either that the ceiling can be exceeded, or that the growth did not start from a stellar mass seed. Both possibilities have been worked on for 2 decades, and both are live. The case for exceeding the ceiling rests on the fact that the Eddington limit assumes spherical symmetry. It assumes radiation pushes outward equally in all directions, against gas falling inward equally in all directions. Real accretion is not spherical. Gas arrives with angular momentum and settles into a disk. If the accretion rate is high enough, that disk becomes thick and optically dense, and something useful happens. Radiation generated in the inner regions cannot escape sideways through the dense material, so it escapes along the rotation axis instead, through funnels of low-density gas at the poles. Meanwhile, gas continues to arrive through the disk plane, where the radiation is not, and is dragged inward faster than it can be pushed out. Some of the radiation is simply swallowed along with the gas before it can do anything at all. Simulations of these thick disks, sometimes called slim disks, suggest accretion at several times the nominal Eddington rate can be sustained, at least in bursts. If the early universe provided dense enough gas supplies often enough, that alone could compress the growth timeline substantially. The problem is that it has to be sustained for a very long time to bridge the gap from 30 solar masses to 100 million, and nothing in the local universe suggests black holes can hold that state for hundreds of millions of years, which leaves the seeds. The direct collapse idea was developed in the early 2000s by a group of theorists including Volker Brom and Abraham Loeb, with important contributions from Mitchell Begelman and from Priyamvada Natarajan at Yale. The proposal is that under a specific and restrictive set of conditions, a cloud of primordial gas can collapse into a black hole without ever becoming stars. The conditions matter and they are strict. You need a halo massive enough that gas falling into it is heated to temperatures where atomic hydrogen can radiate, roughly 10,000 degrees. You need the gas to be genuinely pristine, with essentially no heavy elements, because heavy elements would let it cool further and fragment. And critically, you need to suppress molecular hydrogen, which is the one coolant available in metal-free gas that could take the temperature below the atomic threshold and allow fragmentation into ordinary stars. Molecular hydrogen is fragile. Ultraviolet light in a particular band breaks it apart. So the scenario requires a neighbour, a halo that is already forming stars, close enough that its ultraviolet output floods the collapsing cloud and destroys the molecular hydrogen, but not so close that its heavy elements have contaminated the gas. Under those conditions, the cloud cannot fragment. It collapses more or less as a single object, forming a supermassive star of perhaps 100,000 solar masses, which is unstable and collapses to a black hole almost immediately. Start from 100,000 solar masses instead of 30, and everything downstream becomes easy. Ordinary Eddington limited accretion, with ordinary duty cycles, reaches 100 million solar masses in a few 100 million years without violating anything. There is a third route as well, less discussed but plausible. In an extremely dense young star cluster, massive stars can sink to the center and physically collide with one another faster than they can evolve and explode. The collisions build a single runaway object of thousands of solar masses, which then collapses. This produces intermediate seeds, larger than stellar remnants and smaller than direct collapse, and it does not require the restrictive chemical conditions. For 20 years, all of this was theory with no observational discrimination whatsoever. Then, two results arrived that gave the argument something to hold. The first came from combining the Webb telescope with the Chandra X-ray Observatory. Both pointed at the same enormous foreground cluster used as a gravitational lens. Behind it, magnified, sat a galaxy at redshift 10.1, seen when the universe was around 470 million years old. The Webb data showed the galaxy. The X-ray data showed a bright, compact source of high-energy emission at its center. The team, led by Arkosh Bogdan, identified it as an accreting supermassive black hole, and it is one of the very few objects at these distances detected directly in X-rays. The mass they inferred was somewhere between 10 and 100 million solar masses. What made it important was the comparison with the host galaxy. In the nearby universe, a galaxy's central black hole is typically about 1 part in 1,000 of the mass of its stellar bulge. In this object, the black hole appeared to be roughly comparable in mass to the entire stellar content of its host. That ratio is off by a factor of hundreds from the local relationship, and it is exactly what a heavy seed predicts. If you start with a black hole of 100,000 solar masses inside a small halo, then, for a long stretch of early history, the black hole is disproportionately large relative to its galaxy, and only later does the galaxy catch up. Natarajan and collaborators had made precisely that prediction years earlier. The second result came from the Deep Extragalactic Survey and concerned the object that had been the most distant known galaxy in the Hubble era. Spectroscopy, by a team including Roberto Maialino, found broad hydrogen emission at its center, indicating an accreting black hole of around 1.5 million solar masses at redshift 10.6. Again small for a black hole, large for its host, and again present far earlier than growth from stellar remnants comfortably allows. There is a fourth possibility that hovers at the edge of these discussions, and that I want to name honestly rather than dramatize. Black holes might have formed directly out of density fluctuations in the first fraction of a second after the Big Bang, before there were stars or galaxies or anything else. Primordial black holes have been discussed since the 1970s. There is no evidence for them. There are strong constraints on their abundance across most mass ranges, but they have never been excluded across all mass ranges, and they would solve the seed problem completely. Nobody in the field treats that as the leading explanation, and neither should we. It is on the list because the list is not yet closed. Here is where the black hole story actually stands. There are 3 viable seeding channels and at least 1 viable mechanism for exceeding the growth ceiling. 2 observations now favour heavy seeds over light ones. Meanwhile, the objects that were supposed to be the clearest examples of early black holes, the little red dots, have started behaving in ways that make their masses uncertain again. The convergence, though, is real, and it is the thing worth carrying away from this. The massive galaxy problem and the early black hole problem are almost certainly not two separate anomalies. They are two symptoms of the same condition. The early universe assembled things fast. It assembled stars fast, and it assembled the dark engines at the centers of galaxies fast. And it did so through a mode of formation that the present universe, with its enriched gas and its more sedate mergers, does not appear to practice anymore. Whether that mode requires new physics or merely different conditions is the open question. It is worth saying that the black hole problem did not begin with the Webb telescope. It had been sitting in plain view for more than a decade, and the field had largely learned to live with it. Through the 2010s, wide-field infrared surveys from the ground found a small number of quasars at very high redshift. Quasars are the extreme end of the accreting black hole population, luminous enough to be visible across essentially the whole observable universe. In 2011, a quasar was identified at redshift 7.1, seen when the universe was around 770 million years old, with an inferred black hole mass of around 2 billion times the mass of the Sunday. In 2021, another was found at redshift 7.6, at roughly 670 million years, with a mass estimated at 1.5 billion solar masses. 1 billion solar masses is far beyond anything the little red dots imply, and these objects were confirmed spectroscopically at high signal-to-noise using techniques nobody disputes. The response at the time was that these were the rarest objects in the universe, a handful of extreme outliers sitting in the very deepest gravitational wells, and that extreme outliers are allowed to have extreme histories. Perhaps they had access to unusually rich gas supplies, perhaps they had merged repeatedly, perhaps they were simply the one in a billion case where everything went right. That argument works for a handful of objects. It works considerably less well now, because the Webb telescope has shown that accreting black holes at these epochs are not rare at all. The little red dots are a common population, appearing in every deep field, and they are far less luminous than the quasars, which means they represent the ordinary case rather than the exceptional one. So the problem changed shape. It was never that a few black holes grew implausibly fast. It is that black holes appear to have grown fast routinely, as a normal feature of the early universe, and that the exceptional objects found before were simply the tip of a distribution nobody could see. That reframing is, I think, the more significant of the two black hole results. A single anomaly can be an accident. A population is a mechanism. There is one more property of the little red dots that deserves its own moment, because it is the kind of detail that changes how you picture them. They are almost certainly not isolated. When the deep fields were examined for the positions of the dots relative to everything else, they did not scatter randomly. They showed a tendency to sit in the same regions as the other high redshift objects. In the overdense parts of the early universe where halos were assembling fastest, that is not surprising in itself. What was surprising is how tight the association appears to be, and how frequently a dot turns out, on closer inspection, to sit inside or immediately beside a larger, more diffuse system. In some cases, the dot is embedded in an extended galaxy that would itself have qualified as one of the unexpectedly massive candidates. In other cases, it appears alone, with no detectable host at all, which is stranger. A supermassive black hole with tens of millions of solar masses and no visible galaxy around it does not fit any local template. In the nearby universe, black holes and their host galaxies grow together in a relationship so tight that it has been used as a diagnostic tool for 30 years. The mass of the black hole tracks the mass of the surrounding stellar bulge to within a factor of a few, consistently, across 4 orders of magnitude. At these redshifts, that relationship appears not to hold yet. The black holes are running ahead, which raises a question the field has been circling ever since. Is the local relationship a law, produced by some regulatory mechanism in which black hole and galaxy constrain each other's growth, or is it simply the state a system settles into after 10 billion years, regardless of where it started? If it is the second, then what we are looking at in the little red dots is a very early phase of an ordinary process caught before equilibrium. The galaxies would eventually catch up, the dots would fade as their gas supply is exhausted or expelled, and their descendants would be perfectly ordinary galaxies with perfectly ordinary black holes at the center, indistinguishable from anything else by the present day. That interpretation has a testable consequence, and it is uncomfortable. If every little red dot grows into an ordinary galaxy, the number of massive black holes in the present universe should be considerably larger than we count. If instead, most of them stall, or their black holes turn out to be lighter than the line widths suggest, the arithmetic works. Nobody has closed that accounting yet. The population also has an end. The dots become rare after redshift 4 and effectively vanish by redshift 3. Whatever mode of accretion produced them ran for perhaps 1 billion years and then stopped. That is another thing the present universe does not do, and another reason to think the early universe was not simply a younger version of this one, but was, in some respects, operating differently. There is a wider consequence to all of this that gets less attention than the massive galaxies, and it concerns what the early universe did to itself. For the first few 100,000 years after the Big Bang, everything was ionized. Then the universe expanded and cooled enough for protons and electrons to combine into neutral hydrogen atoms, which is the moment the microwave background was released. And for a long stretch afterwards, space was filled with neutral gas and essentially no light sources. That period is genuinely called the Dark Ages, and the name is literal rather than poetic. Then the first stars ignited, and their ultraviolet light began stripping electrons back off the hydrogen around them. Bubbles of ionized gas grew around the earliest galaxies, expanded, met, and eventually merged until the entire intergalactic medium was ionized again. That transition is called reionisation, and it is the last global phase change the universe has undergone. We know roughly when it finished. Light from distant quasars passing through intergalactic gas gets absorbed at wavelengths corresponding to neutral hydrogen, and by examining how that absorption changes with distance, we can trace how much neutral gas remained at each epoch. The picture that emerges is that reionisation was largely complete by around redshift 5.5 to 6, when the universe was about 1 billion years old, with the process stretching back to somewhere around redshift 10 or beyond. The question that occupied the field for 20 years was what did it? Quasars produce enormous quantities of ionising radiation, but there are not many of them at those distances. The consensus that formed before the Webb telescope launched was that the work was done by vast numbers of small, faint galaxies, each contributing a modest amount, with the additional requirement that a reasonable fraction of the ionizing photons produced inside those galaxies actually escaped rather than being reabsorbed by gas in the galaxy itself. That escape fraction is a genuinely hard quantity to measure, because at these distances the relevant photons are absorbed on the way, estimates clustered around 10 to 20%, and the whole budget balanced only if the faint end of the galaxy population extended a long way down. Then the Webb telescope found more ultraviolet bright galaxies at high redshift than anyone had budgeted for. The consequence is not obviously a good thing. More galaxies, brighter, earlier, means more ionizing photons produced sooner. Combine the observed abundance with the standard escape fraction and the standard photon production rate, and reionization finishes considerably earlier than the quasar absorption data says it did. This has been called the photon budget crisis, and it is a real constraint rather than a rhetorical one. It cuts against the interpretation that everything can be resolved by making early galaxies less massive, because the budget problem does not depend on stellar masses at all. It depends only on how much ultraviolet light is coming out, and the ultraviolet light is measured directly, so we have an odd situation. If you reduce the stellar masses by invoking a top-heavy initial mass function, you make the light-to-mass problem better, and the photon budget problem worse, because top-heavy populations produce more ionizing radiation per unit mass, not less. The corrections that ease one tension can aggravate another. The way out that the field has largely converged on is that the escape fraction must be lower than assumed, or that it varies strongly between galaxies and over time, or that the bursty behavior we discussed cuts the duty cycle down. Each of those is plausible. None is measured. The Webb telescope also produced a set of results about the early universe that are strange in ways unrelated to mass, and I want to place a few of them here because they change the texture of the picture. The chemistry is wrong in interesting places. The galaxy that held the Hubble-era distance record, examined spectroscopically at high resolution, shows a ratio of nitrogen to oxygen far higher than anything expected in a young system. Nitrogen is produced in a particular way in intermediate mass stars over relatively long timescales and having a great deal of it a few 100 million years after the Big Bang is difficult to arrange with ordinary stellar populations. One class of explanation invokes supermassive stars, objects of thousands of solar masses forming in extremely dense clusters, which would produce exactly that abnormal enrichment pattern. Similar nitrogen enhancements have since turned up in other early objects and in some ancient globular clusters in our own galaxy, which may or may not be the same phenomenon. The morphology is also further along than expected. Before the Webb telescope, the assumption was that early galaxies were chaotic, clumpy, disordered, dominated by mergers and turbulence, with orderly rotating disks only assembling much later. What the deep imaging showed was a substantial population of orderly, rotation-dominated disks at redshifts of 4, 5 and beyond, and a fraction of galaxies with clear central bars, which are structures that require a dynamically settled disk to form at all. Radio observations from the Atacama Large Millimeter Array, which can measure the motion of cold gas directly, confirm genuine ordered rotation in some of these systems. So it is not only that early galaxies were more massive than predicted, they were also more structured, settled, organized in ways that the standard picture reserves for a later, calmer era. And the abundance of the brightest objects has not fallen off with redshift the way it should. In the standard picture, the number of ultraviolet bright galaxies should drop sharply as you look further back, because the halos capable of hosting them become exponentially rarer. What the surveys have found is that the decline is much shallower. The excess of bright galaxies relative to pre-launch predictions persists all the way to redshift 14, at the very edge of what can currently be reached. It is worth adding, in fairness to the previous generation of astronomers, that none of this was completely without warning. Through the 2010s, infrared observations with the Spitzer Space Telescope had identified a population of unexpectedly massive and unexpectedly quiescent galaxies at redshifts around 4 to 6, galaxies that had apparently formed their stars early and then stopped. Those results generated their own smaller version of this argument at the time. They were sometimes dismissed as marginal detections at the limit of a small, warm telescope's capability. They were not marginal. The Webb telescope has confirmed several of them and found that the population extends further back and is more common than the Spitzer data could show. The field had been receiving this signal for a decade and had found reasons not to act on it, which is a very ordinary thing for a field to do when the signal is faint and the framework is comfortable. There is one more result from this period that I keep returning to, because it is the cleanest single measurement of the whole affair, and it does not depend on any fitting code at all. The galaxy that currently holds one of the highest confirmed redshifts, seen when the universe was around 300 million years old, was observed not only by the Webb telescope, but by the Millimeter Array in Chile. The millimeter observations were looking for a specific emission line from ionized oxygen. They found it. That single detection does two things at once. It confirms the distance independently, because an identified emission line gives a redshift with essentially no ambiguity, and a millimeter line measured from the ground is about as different from a space-based photometric fit as two measurements can be, and it tells you that the galaxy already contained oxygen. Oxygen is not primordial. The Big Bang produced hydrogen, helium, and a trace of lithium. Every oxygen atom in the universe was made inside a star and released when that star died. For a galaxy 300 million years after the beginning to contain a substantial quantity of it means that a full cycle has already completed. Stars formed, lived, exhausted themselves, exploded, and dispersed their contents into gas that then formed more stars. And the quantity was higher than expected, by something like a factor of 10 relative to what models predicted for a galaxy of that age. This is the same story in a different medium. Not stellar mass, not black hole mass, not luminosity, but chemistry. And it points in the same direction. Whatever was happening in the first few 100 million years was happening faster and more thoroughly than the models allowed. It is also the result that is hardest to argue with, because it is a line detection rather than a fit. You either see the line at that wavelength, or you do not, and they did. Which leaves the last of the escape routes, and the least popular one. What if the framework itself needs adjusting? The standard model of cosmology is not a single claim. It is a small set of parameters, about 6 of them, from which an enormous amount follows. The density of ordinary matter, the density of dark matter, the expansion rate, the shape of the primordial fluctuations. A couple of others. Fix those 6 numbers and you can predict the pattern of ripples in the microwave background across every angular scale, the relative abundances of hydrogen, helium, and lithium produced in the first 3 minutes, the way galaxies cluster today across billions of light years, and the brightness of exploding stars at every distance. It does all of that with 6 numbers, and it has been doing it for 30 years while people have tried very hard to break it. So the bar for modifying it is properly high, and the proposals that have been made in response to the early galaxy problem are worth walking through, partly because several of them fail in instructive ways. The most commonly suggested change is to make the dark matter warm rather than cold. Warm dark matter particles move fast enough in the early universe to stream out of small overdensities before they can collapse, which erases structure below a certain scale. This has been proposed for years as a solution to various problems concerning the number of small satellite galaxies around the Milky Way. It does not help here. It makes things worse. Suppressing small-scale power means the first halos form later, and there are fewer of them, which delays galaxy formation rather than accelerating it. If anything, the Webb results tighten the constraints on how warm the dark matter can possibly be. This is a good example of an anomaly ruling something out rather than in. Self-interacting dark matter, in which dark matter particles scatter off one another, changes the internal density profiles of halos but does very little to their abundance. It is largely irrelevant to this problem. A more interesting candidate is early dark energy. This was proposed for a different reason entirely, as a way to ease the Hubble tension, the disagreement about the current expansion rate that we touched on earlier. The idea is that some additional energy component was present around the time the microwave background was released and then decayed away quickly. If it existed, it would have altered the timing of structure growth, and some versions of it do produce more early massive halos. It is attractive because it would kill 2 problems at once. It is also constrained fairly tightly by the detailed shape of the microwave background power spectrum, and the versions that best solve the Hubble tension are not obviously the versions that best help here. Then there is a proposal that gets less attention but is, to my mind, the most elegant of the lot. The standard model assumes that the primordial density fluctuations were Gaussian, that is, their statistical distribution is a simple bell curve with no skew. This is what the simplest models of inflation predict, and it is consistent with everything measured so far. But if there is even a small departure from Gaussianity, with a slight excess in the high tail, the effect on rare objects is dramatically amplified. Massive halos at high redshift are, by construction, drawn from the extreme tail of the distribution. Fatten that tail slightly, and the number of the very rarest objects can change by orders of magnitude, while the typical objects, and therefore the microwave background, barely move at all. That is a genuinely appealing property because it changes exactly what needs changing, and nothing else. It also makes a testable prediction. Non-Gaussian initial conditions leave a distinctive signature in how galaxies cluster on very large scales, and that signature is measurable with wide surveys. A related option is a small tilt in the primordial power spectrum, giving slightly more power on the scales that formed the first galaxies. The microwave background constrains the tilt across the scales it can see, but the relevant scales for the first galaxies are smaller, and the extrapolation there is not directly verified. Each of these is on the table. None of them has independent support. And they all face the same structural objection, which is that they would need to produce a large effect on early galaxies while producing no detectable effect on the many other things the model already gets right. The majority view in the field, as far as such a thing can be assessed, is that the resolution will be astrophysical rather than cosmological. The reasoning is not merely conservatism, and it is worth stating clearly. The cosmology, the part governed by those 6 numbers, is the clean part of the theory. Gravity, acting on a nearly uniform fluid, is a problem physicists can actually solve. The messy part is everything that happens to ordinary matter afterwards. How gas cools, how clouds fragment, what mass stars form with, how supernovae couple their energy to their surroundings, how black holes regulate their hosts. Those processes span an enormous range of scales, cannot be simulated from first principles, and are represented in every large cosmological simulation by approximations tuned to reproduce the present-day universe. If a tension appears between prediction and observation, the honest prior is that it lies in the part of the theory built from tuned approximations, rather than the part built from 6 measured numbers. That said, holding that prior too tightly is exactly how a field misses something. The Spitzer results were dismissed with essentially the same reasoning. So let me lay out the scoreboard as plainly as I can, because in a story like this, the honest inventory is more useful than any conclusion. We know that the Webb telescope has found a population of bright, apparently massive galaxies at redshifts between 7 and 9, in place when the universe was between 500 and 700 million years old. We know they are more numerous and more luminous than the models predicted, and that the discrepancy is not marginal. Depending on which sample and which model you compare, the excess runs from a factor of several to a factor of 10 or 20. We know that the excess of ultraviolet bright galaxies persists to the highest redshifts currently reachable, past 14. We know that the little red dots are a real population, that many host accreting black holes, and that those black holes appear to be enormously overweight relative to their host galaxies compared with the local relationship. We know that the same objects are almost invisible in X-rays and almost non-variable, which is not how accreting black holes are supposed to behave, and that their interpretation is currently being rewritten. We know that some early photometric redshifts were badly wrong. A candidate at redshift 16 turned out to be at 5. Maisie's galaxy came down from 14 to 11.4. One of the original 6 massive candidates turned out to be a dust-buried black hole at redshift 5.6. We know that stellar masses derived from photometry and even from spectroscopy carry uncertainties of at least a factor of 2 or 3. From the initial mass function, from the star formation history, from black hole contamination, and from dust. We do not know whether those uncertainties taken together are enough. They are plausible. They are not demonstrated. And a resolution that requires 4 separate corrections all running the same direction on every object is not yet a resolution. We do not know what the little red dots are. We do not know how the first supermassive black holes were seeded, though the evidence has shifted toward heavy seeds. We do not know whether the standard cosmological model needs revision. It has survived every previous challenge. This is the most serious test it has faced in decades. A serious test is not a refutation. And we do not know how long it will take to find out, though the tools are being pointed at the question now. Longer wavelength imaging that can separate stellar light from black hole light. Millimeter observations that weigh galaxies by their cold gas rather than their starlight, giving an independent mass entirely. Wide surveys that will find enough of these objects to measure their clustering, which would discriminate directly between astrophysics and non-Gaussian initial conditions. Deeper spectroscopy of the dots. The answers will come. They are not here yet. I want to spend a little time on the people, because the shape of this argument has been unusual, and the way a field behaves under pressure is part of the story. The volume alone was extraordinary. In the first 18 months after the telescope's science operations began, the rate of papers using its data ran to several hundred per year, and a large fraction of them concerned the first billion years. Preprints appeared within days of data becoming public. Some of those early papers were wrong, and their authors knew there was a reasonable chance they would be wrong when they posted them. The calculation was explicit. Publish fast with appropriate caveats and be corrected, or publish carefully and be scooped. That is not a flattering description of scientific practice, but it is an accurate one, and it produced a genuine cost. The redshift 16 candidate that turned out to sit at 5 was reported widely as a record before anyone had a spectrum. When it collapsed, the correction received a fraction of the attention the original claim had. It also produced a genuine benefit, which is that the community identified and corrected its own errors at remarkable speed. The spectroscopic follow-up that killed several of the most extreme candidates was conducted, in some cases, by the same people who had proposed them. The most interesting thing about the argument, though, is who was on which side. The astronomers with the deepest investment in the pre-Webb picture were not the ones defending it hardest. Garth Illingworth, Richard Bowens, Pascal Oesch and their collaborators had spent 2 decades establishing that early galaxies were small and faint. They had built that picture from images that took hundreds of hours each. If anyone had reason to resist the new results, it was them. Instead, they were among the people doing the careful spectroscopic work that both eliminated the false candidates and confirmed the surviving ones. Illingworth, in interviews around this period, was direct about it. He described looking at the new data and recognizing that a substantial part of what he had spent his career establishing was going to need revision, and treated that as the expected outcome of building a better instrument rather than as a loss. That is worth pausing on, because there is a version of this story where the establishment digs in, and it did not happen. The pushback came from methodological grounds, and it came from people across the field, including from the authors of the original claims. There is a conference in the summer of 2023 that people who were there still refer to. Theorists presented calculations showing that the observations, taken at face value, required either new physics or star formation efficiencies nobody had ever seen. Observers stood up and said, in effect, that the theorists were putting far more weight on the mass estimates than the observers themselves would. The sessions ran long. Attendees described the tone as intense but not hostile, which is the description of an argument where the participants believe the answer exists and expect to find it. No resolution was reached. That was, arguably, the correct outcome. The data was not sufficient to settle it, and everyone knew that. Let me put you somewhere for a moment, because I think the physical situation is worth inhabiting. You are sitting in front of a screen. It is late, because the data pipeline finished processing overnight and you wanted to look before the morning meeting. On the screen is a section of the deep field, grayscale, enlarged until individual pixels are visible as squares. The object you are looking at occupies perhaps 9 of those squares. It is not bright. Against the background noise, it is a slight, dirty smudge, the kind of thing you would dismiss as an artifact if the pipeline had not flagged it in 4 separate filters. In the 2 shortest wavelength filters, it is not there at all. Not faint, absent. That absence is the entire measurement. The neutral hydrogen of the early universe swallowed everything blueward of a particular wavelength, and the position of that cutoff, translated through a piece of arithmetic that fits on one line, tells you when the light left. You know, sitting there, that the photons producing those 9 grey squares departed their source before the sun existed, before the cloud that became the sun existed. They crossed a universe that expanded by a factor of 9 underneath them while they travelled. And you know that if the numbers coming out of the fit are right, that smudge contains as much stellar material as everything around you, everything you have ever seen in the night sky, every star in the Milky Way put together. There is nothing to feel. No sense of scale arrives with the data. The screen looks exactly the same as it would if the object were a nearby dwarf galaxy or a detector fault. The only thing that has changed is a number in a column, and your understanding of what the number means. That is what the work is actually like. The universe does not announce itself. It arrives as a slight excess of counts in a few pixels, and someone has to decide whether to believe it. The astronomer in the dark room with the cream circle believed it enough to check, then checked again, then handed it to someone with a more conservative code who checked it a third way, then published it with the word candidate in the title, because that was the honest word. 3 years on, some of what she circled has dissolved and some of it has hardened, and the part that hardened has not gone away. There is one thing the telescope was built to find that it has not found, and its absence sits underneath every argument in this story. Nobody has ever seen a first-generation star. The theory is detailed. Sometime in the first 200 to 400 million years, inside small halos of perhaps 100,000 to 1 million solar masses, gas made only of hydrogen and helium began to collapse. With no heavy elements, the only available coolant was molecular hydrogen, which is a poor one. The gas could not shed heat efficiently, so it stayed warm, so it could not fragment into small pieces. The characteristic mass at which a cloud becomes unstable and collapses scales steeply with temperature, and in that pristine warm gas the characteristic mass was enormous. The result, according to the simulations, was stars of tens to hundreds of solar masses, blazing hot, blue-white, producing prodigious ultraviolet output, and living perhaps 2 or 3 million years before exhausting themselves. On a cosmic timescale that is instantaneous, they lit, they enriched, they died. The most massive of them died in a way that no star in the present universe can. Above a certain mass, the core becomes hot enough that photons begin converting spontaneously into electron-positron pairs. That conversion removes radiation pressure from the core, which causes the star to contract, which raises the temperature further, which accelerates the process. The star collapses and then detonates completely in what is called a pair instability supernova, leaving no remnant at all. No neutron star, no black hole. The entire mass is dispersed. Those explosions leave a chemical fingerprint that is genuinely distinctive. They produce a strong alternating pattern between elements of even and odd atomic number, and they produce essentially none of the heavy elements formed by neutron capture. If you can find gas or a later star carrying that signature, you have found the ashes of a first-generation star, even if you never see the star itself. That is the strategy that has been pursued for 30 years, and it has come tantalizingly close. Surveys of our own galaxy's halo have found ancient stars with iron abundances less than 1 part in 10 million of the sun's, which is about as close to primordial as anything observed. Several of them carry abundance patterns, consistent with having formed from the debris of a single earlier supernova. But those are second-generation stars at best. The first ones themselves are gone. The Webb telescope has produced candidates. There have been reports of pockets of gas at high redshift with helium emission and no detectable metals, which would be the direct signature of pristine star formation, in some cases seen through the magnification of a foreground cluster. There have been claims of first-generation signatures in individual clumps within lensed galaxies. Each has been debated. None has been established to the field's satisfaction. The reason this matters for everything else in tonight's story is that the initial mass function of the earliest stars is precisely the assumption doing the most work in every mass estimate we have discussed. If first-generation star formation, or something close to it, persisted longer and more widely than assumed, then the light-to-mass conversion at these redshifts is wrong in a specific and calculable direction. The impossible galaxies become merely surprising. So one of the largest uncertainties in the whole problem concerns objects that theory describes in detail and observation has never touched. That gap is not a failure. It is simply where the boundary currently sits. The first stars are faint, brief, and rare, and finding them may require either far deeper observations, an extremely fortunate alignment of a foreground lens, or an instrument that does not yet exist. So what would actually settle this? It is a fair question, and it has concrete answers, which is one of the more reassuring things about the situation. This is not a mystery in the sense of something unreachable. It is a problem with a queue of instruments already pointed at it. The first is the telescope itself, used differently. The mid-infrared instrument aboard the Webb Observatory sees at wavelengths long enough to capture light from older, cooler, low-mass stars, which is where most of a galaxy's stellar mass actually resides. Ultraviolet and optical light, which is what the near-infrared camera collects at these redshifts, is dominated by a small number of young massive stars and is therefore a poor guide to total mass. Mid-infrared observations of these objects are expensive because the instrument is less sensitive and the exposures are long, but they measure the thing that matters. Several campaigns have been carried out and more are underway, and the early returns generally pull masses downward while not eliminating the excess. The second is millimeter astronomy. The Atacama Large Millimeter Array, an array of 66 antennas on a plateau in northern Chile at 5,000 meters altitude, detects the cold dust and molecular gas in galaxies rather than their starlight. That gives an entirely independent handle on mass, one that does not depend on the initial mass function, on the star formation history, or on any assumption about stellar populations at all. If millimeter observations of these objects return gas masses consistent with the high stellar masses, that is very difficult to explain away. If they return low gas masses, that is informative in the opposite direction. The third is statistics. Individual objects can always be argued about. Populations are harder to dismiss. Wide field surveys covering far larger areas than the current deep fields will find these objects in numbers, and numbers allow you to measure how they cluster. This is the crucial test, because the competing explanations make different predictions about clustering. If the massive objects are ordinary galaxies caught during bursts, they should sit in ordinary halos and cluster accordingly. If they are genuinely rare, extremely massive systems, they should sit in the deepest gravitational wells and cluster far more strongly. And if the initial conditions were non-Gaussian, the clustering signature on very large scales is different again, in a way that nothing else mimics. The Nancy Grace Roman Space Telescope, designed to image an area of sky hundreds of times larger than the Webb telescope can cover per exposure at comparable depth, is the instrument built for exactly that kind of census. The fourth is ground-based spectroscopy at scale. A generation of extremely large telescopes with primary mirrors between 25 and 39 meters across is under construction, and their light collecting area will make it possible to take detailed spectra of objects that currently require the Space Telescope's entire attention for hours. The fifth concerns the black holes specifically, and it does not involve light at all. When two supermassive black holes merge, they radiate gravitational waves at frequencies far below anything a ground-based detector can sense, because the relevant wavelengths are comparable to the size of the Earth's orbit. A space-based detector consisting of 3 spacecraft, separated by millions of kilometers, trading laser beams and measuring the distances between them, would detect mergers of black holes of exactly the mass range in dispute, out to the redshifts in dispute. That measurement would tell us the mass distribution of early black holes directly, without any inference from line widths or luminosities. The mission is planned. It is not close. None of these will produce a headline that resolves everything in one morning. What they will do is narrow the space, one constraint at a time, in the ordinary way. And it is worth saying plainly that the most likely outcome is not the dramatic one. Most anomalies in the history of astronomy have resolved into astrophysics rather than new fundamental physics. The excess of high-energy cosmic rays, the missing satellite galaxies, the anomalous rotation of certain systems, the early quasars found in the 1960s that also seem to have formed too fast. Each of those generated its own period of excited speculation, and most of them turned out to be a matter of understanding messy processes better. But not all of them did. Dark matter itself was once an anomaly in a rotation curve that most of the field expected to resolve into ordinary astrophysics. That is the honest position. The precedent runs mostly one way, and the precedent is not evidence. The image is still there, if you close your eyes. The dark room, the monitor, the only light in it, the deep field filling the screen, thousands of tiny galaxies scattered across the black, each one a system of stars, each one photographed at a different moment in the history of the universe, because each one is a different distance away. Nothing in that image is simultaneous. It is not a photograph of a place. It is a photograph of a great many separate times, arranged by accident of geometry into something that looks like a single view, and somewhere in it, the red smudge with a thin cream ring drawn around it. It does not look like 100 billion suns. It does not look like a challenge to cosmology or a puzzle that will occupy a generation. It looks like a smear, 9 grey pixels, and a slight excess of counts in the longer filters. If you did not know what you were looking at, you would scroll past it. 3 years of argument have moved a good deal around it. Some of the objects in that first sample turned out to be something else. Some of the most spectacular candidates from those first months collapsed under spectroscopy into ordinary galaxies at ordinary distances. The masses came down. The error bars grew. The word crisis appears less often in the literature now than it did in 2023, and that is appropriate, because a crisis is a thing that happens quickly, and this is not happening quickly. But the core of it has not moved. The early universe produced more and brighter and more finished objects than the models said it could, at a time when it should have been producing almost nothing. Every correction that has been applied has reduced the excess. None of them has removed it. And underneath all the argument about initial mass functions and duty cycles and escape fractions and seed masses, there is one fact that does not depend on any of them, because it does not depend on a model at all. It is a fact about time. The Earth formed roughly 4.5 billion years ago. For most of that history, it had no grass on it. Grass is recent. It shows up in the fossil record around 66 million years ago, near the end of the dinosaurs, and it took the planet something like 4.5 billion years of oceans and volcanoes and bacteria and forests and extinctions to arrive at a lawn. The galaxies in that image assembled 100 billion stars in 600 million years. I do not think that comparison gets easier the longer you hold it. It is not that one number is larger than the other. It is that the intuition we carry about how things grow, that big things take long times and small things take short ones, has no purchase here at all. A blade of grass sits at the end of a longer causal chain than an entire galaxy. We built a telescope to look at the beginning. It took 30 years, cost $10 billion, was nearly cancelled by a committee, and depended on 344 mechanisms unfolding perfectly 1,000,000 miles from anyone who could help. We pointed it at the darkest patches of sky we could find, and we asked for the baby pictures. We got them. They are there. At redshift 13 and 14 and beyond, the small, ragged protogalaxies are exactly where the theory said they would be. Faint and blue and unformed, doing what infants do, but scattered among them, in a universe that had barely started, there were things that were already finished. Bright, heavy, ordered, old. Good night.